Good afternoon, everyone. I am Olivier Caumont from CNRS Météo France, and we will start the next session. So it's about some results that we can obtain when we combine the models, either meteorological or hydrological. Here are the session's objectives. So first, the idea is to contrast the ways of doing hydrometeorological science with or without e-science infrastructures, such as the one of DRIHM. The second objective is to give you an overview of the practical applications that we can get when using such infrastructures before you go into details in the next sessions, where you will learn how the models work, how you can couple them, and so on. And the third objective is to try to demonstrate to you that such e-science environments are useful to advance science. So, and we will show you this on a serious use case, something that I will introduce later. So the scope, and actually the plan also. First, I will show you the GNOAA 2011 flash flood, which is a DRIHM critical case, in which was already introduced in the previous session by Nicolas, among others. And then I will present very briefly the meteorological models and the hydrological models that I will use. And here, for the sake of simplicity, I won't talk about hydraulics. So if you remember, this is the general idea of DRIHM. You know, it's to start from rainfall sources, which can be given by observations or meteorological models, and to go down to hydrological models, typically rainfall runoff models, and then go down to hydraulic models and impact models. So here, I will just only show you stuff regarding these aspects, okay? I won't talk about this. Okay, and finally, I will try to put the emphasis on the benefits that we can gain from such infrastructure. Okay, so the GNOAA case. It was already presented by Nicolas, so I don't know how much I have to go into details. I will do it very briefly. Here on the left, this is large-scale fields at upper level. It's derived from the IFS analysis. IFS is the model of the European Center for Medium Weather Forecasts. And actually, it gives you a rough idea of the general circulation, the general synoptic circulation. So for instance, you can typically the winds follow these isolines here, and you can see that in GNOAA, which is located here, we have southwesterly winds in the upper levels, and it's a different flow which is favorable for large-scale ascents. And if we look at more local conditions here, it's near the ground at 950 hectopascals. Actually, it's a zoom here over this area. You can see that there are two main flows. The one come here from the Po Valley, and it's colder. It's denoted by the color here. And there is another one which is actually warmer and moister as well, and which is coming here. And when these two flows meet, then it can trigger convection, deep convection, and you get thunderstorms. And this is actually what happened on this day. And you can also have an interaction with the mountains, where the flow comes toward the mountains and is deflected towards upwards. So this is what happened in that days. Here it's the radar mosaic of reflectivities, gives you a rough idea of the precipitation that occurred on this day. So you can see here from 1 UTC here, you have a very strong convective system here, and which is affecting this area here where Genoa is lying. And you see that this convective system, as during the day, is moving first eastwards and then westwards along the coastline. And in the end, you get this map that you have already seen, which gives a very large amount here on over Genoa with 450 millimeters in one day. And there is a lot of contrast because, for instance, in these areas, you only get 25 millimeters. So you can see already that it could be a challenge to forecast such event. Okay, and so yes, just to say that in the end, the Bizango Creek, which flows through Genoa, burst its banks and it flooded the city. So some images here you can see. This is very similar to another event that occurred in 1970 and which killed 25 people. So it's the worst event since then. Okay, so now I will go to the models. So first, the atmospheric models. So these are the models we have used for this study. There is WRF NMM, WRF ORW, rainform, mesoNH, and AROM. I won't go into the details. You will see more details in the next sessions about some of these models. I just want to point out that these models are very different. In particular, they have different domains, initial and boundary conditions. So here I show you the domains of the models. So you see, for instance, this one in yellow is the domain of AROM. mesoNH is in red here, WRF NMM, and WRF ARW. And they also have different boundary conditions. The horizontal resolutions range from 50-100 meters to 4 kilometers. They have different projections, different types. There is a stochastic downscaling model, rainform, and the others are physically based. The dynamical cores may be different. For instance, it's the main difference between WRF NMM and WRF ARW. And the physics also can be different. And there are some models which are only deterministic and some others which can also be run in a probabilistic way, which means you have different members, different scenarios. And finally, they have input and different input and output formats. So for the hydrological models, we have HBV, drift, and rifts, and it's the same story. They are very different also regarding the physics and forecast modes, deterministic versus probabilistic. And also the formats are different. Okay, so now if we didn't have such any infrastructure such as the DRIHM one, we were only able to do such chainings. That is, between WRF ARW and drift, and WRF ARW rainform and drift. Because, for instance, these other models were not calibrated for the Bizango basin. And, for instance, there was no interface between mesoNH and drift and so on. So these models couldn't be chained only because there was a dedicated direct hardwired coupling. So now I go to the benefits gained from the infrastructure. So from the last diagram, we move to this one, where we introduced, so in a simplified manner, some standard interfaces. So for greedy data, it was an ATDF-CF, which was adopted. So now we are able to basically couple every meteorological model with every hydrological model. What is also interesting is that we can use rain farm driven by any meteorological model. We didn't do it, but we could do it. And also, it's much easier now to compare the outputs of these models because they are all in the same format. And this is what I will show later. Okay, and just to finish here, we also introduced another standard for time series, point series data, which is WaterML2, and it also allows us to compare the models with each other. Okay, you already saw this this table. It's the summary of all model configurations which were used in this study. So you have the list of rain sources here, and with the description here, I won't go into detail. And just to show you that some of these models can be run in a probabilistic manner, so we have many ensemble members. And if we combine them with the hydrological models which are here, you get these figures here, and in the end, you end up with more than 1,600 different hydrometeorological scenarios. So this is interesting to have a lot of simulations, but what for? And this is what I will show you now. So for the meteorological part, you've already seen that before, but just to point out that here the models are different, but they also give very different scenarios. So you get, for instance, the maximum of precipitation either on the west side or on the eastern side of the Bisagno basin, but only a few models actually give the maximum of precipitation amount over the right area here. So this was already mentioned before. Okay, so this is to show you how the DRIHM infrastructure can help you to compare different models. Actually, when you don't have the same formats, usually you end up with something like this. This is to measure a temperature from the DRIHM model at a given time, and for the same time you have the same physical quantity, but actually for a different model. And these models don't have the same projections, the same formats, and so on, so usually you cannot compare them easily. So when you have the same formats, you can do this, and obviously much easier spot the differences between the models. For instance, we see here the effect of the resolution. This model is at 2.5 kilometer resolution, while this one is at 500 meter horizontal resolution. You can also see many different things, small scale effects and so on. So what you can do also is compare, finally, the scenarios that you get. So for instance, here you can once again see the impact of the resolution. This model has the coarsest resolution of all three here. And what you can see is that the convective system here is not located at the same place at the same time in all simulations. And actually, when you have the same formats, you can plot as many fields as you want. And you can see here, this is the wind near the ground, and in color this is the speed. You can see here the convergence line, which is associated with the convective system. And actually, you can see that in these models, this one gives the best results because the convergence line is more to the west than in the other models. So it's very interesting for process studies to have such common formats and such common visualization tools. So it's also interesting to compare different ensembles and different, rather than only different models. Here on the top panel you have rainfall time series, which are averaged over the largest common domain. And this is here the hourly precipitation accumulation, and here the total accumulation since the beginning of the day. So you can see that for these different models you have some spread, and you see that they don't give the same here. Best one being meso-NH, you can see, but it's meso-NH. It's also interesting, as I said, for ensembles. Here it's the same, but for two ensembles. In red, this is the meso-NH ensemble, and you can see that there is not much spread for the precipitation forecasts, while in the AROM ensemble here, you have more spread during the day and also in the total accumulation. Well, actually, it's more or less the same order of magnitude. But if you do that for the Bizengo catchment, so at a smaller case, you get, at a smaller scale, you get different conclusions. For instance, if you look at these two ensembles, you get more spread for the meso-NH ensemble, and you get accumulations which are very close to the observed ones. I didn't say it, but in black it's the observation. While for the AROM ensemble, you have not much spread, and actually you underestimate a lot the total precipitation accumulation. Okay, so now I move on to the hydrological part. For instance, you can compare the discharge time series from the different hydrological models. So in green, this is RIPS. In red, this is HBV, and in black, this is drift. This is done the use of a common format. So in blue, you also have the observation, and you see that for this case, the best hydrological models, which are, sorry, I didn't mention it, they are all driven by the observation, by the rain gauge observations. They give the best hydrological models are drift here and RIPS, because they give a maximum discharge which is close to the observation. While HBV gives something which is not that important. Okay, I think you already saw that, so I will move on quickly. It's just a way of presenting hydro-meteorological results. So in the upper panel, this is the rain source. So in black, this is the rain that was observed in the past. In blue, this is the rain that will be observed, and in red, this is the rain which is forecast. So in the lower panel, this is the discharge, and of course, this is the same color for the corresponding discharge. And when you move on, you can simulate the predictions that would be done in real time, actually. Okay. Okay, so here, this is. These are some slides to show you that you can carry out some sensitivity experiments to one of the components of the hydrometeorological chain. So for instance, here you can compare different rainfall, which means you take the same hydrological model, which is drift here, in the two panels, but in the upper panel you drive it with an AROM simulation, for instance, while in the lower panel, you drive it with a meso-NH simulation. You can do the same by you can carry out a sensitivity experiment to the hydrological model as well. So for instance, here, if we keep drift and meso-NH, so here we can change drift for rips and obtain different pictures that we can compare quickly. This is interesting to assess how much uncertainty is associated with each of the components. Okay, so in the end here it's just to show that you can combine an atmospheric ensemble with, okay, here this is a deterministic hydrological model, and you can combine both ensemble here. So you have a meteorological ensemble and a hydrological ensemble. So you get all this spread here. Okay, last set of plots. Here, this is to show you in a probabilistic way study the sensitivity to the hydrological model. So here you have the discharge, and here a probability of non-exceedance. And for each curve here corresponds to the meso-NH ensemble that drove either in one, this is the deterministic rips, in two, this is the rips ensemble, in three, this is drift, and in four, this is HBV. Okay, and this plot shows that, for instance, if you set a threshold of 400 cubic meter per second as a warning threshold for flash flood, you see that all these models, 1, 2, and 3, all these chains give a non-zero probability that you will exceed this threshold. So you can do it in a reverse way, which means you take one hydrological model and you drive it with different models, meteorological models, and you get a similar picture here, where you can see that, for instance, in this case, 4, 7, and 5, which are the meso-NH ensemble, rain farm, and another meso-NH ensemble give significant probabilities that you will exceed this threshold. Okay, and of course you can do it also for different hydrological models. So here you see that when you change the hydrological models, you get less chance to have a significant flow. And if you change to HBV, if you remember when it was driven by the observations, this is the model that gave the least maximum discharge. So you can see that for this model there is no hydrometeorological chain which gives significant exceedance probabilities. Okay. So I will sum up all the benefits that we have seen so far, and I've split them into technical and scientific benefits. So first, the technical benefits are that we are able to produce a large multimodal ensemble of hydrometeorological forecasts. If you remember, this was this table, this blue table with lots of runs. The use of the DRIHM infrastructure allows us to compare easily all the models with each other. It also allows us to combine the models together. I'm not sure I've shown that, but it's possible since we have the same formats. And it also allows to carry out sensitivity studies to each component of the hydrometeorological chain. So regarding the scientific benefits, such infrastructure is very useful for process studies such as predictability, also the identification of key processes, and also, for instance, sensitivity studies to parameterizations and so on. It also allows to evaluate the respective performance of each of the models and ensembles, and also of a combination of these models and ensembles. It's been shown for other multimodal hydrometeorological chains that when you combine different ensembles together, you always get a better added value than using only one ensemble, even if this ensemble is more than the others. And in the end, it's a useful tool to guide you in the design of an operational hydrometeorological forecasting chain. Just for instance, by calibrating the ensembles or merging or combining them together. Okay, and that's all. If you have questions, I'll be happy to answer them. We have some minutes.
Slide 19. Yes, it's the one related to different resolutions, different domains, and so on. Okay, here. I wonder, maybe this will explain also my next presentation. Are the number of ensemble members resolution due to specific features of the models, or is it just by chance? For example, why only one run with Wolf and 10 with Metro and Age? Why different resolutions?
Okay, so you are asking why there are different resolutions for each of the models. In the ensemble members. So, second question. All ensemble members have the same resolution. I think it's usually done this way. I've never seen an ensemble which is run with different resolutions. And the why different members? Number. Okay. Why? Well, it's more or less arbitrary because there were already some simulations which were available, so we chose just to take them, and we didn't try to have everything in the same. And also, it's very interesting because to have, to change as many things as possible when, for instance, you try to have to simulate a case in the best way. You have to try very different things, like the initial time, the boundary conditions, and so on. So it's not that good to have something too homogeneous to get the best simulation. Yes?
When you have 1,600 combinations,
yes,
would you run them all? Because after all, it's about computational time. Or you would find a way to select scenarios which are less or more disastrous, let's say, and to build a funnel of them, I don't know.
So you're wondering how we can pick up in those in all these scenarios. Well, actually, I would say it depends on what you want to do, on your goal. If you're looking at the best simulation, then it's not very difficult. You just compute skill scores and so on, and you look at the forecasts, and you select the best one. But if you're more interested to build, for instance, an operational hydrometeorological system, then you have to look at other things. You have to look, for instance, at some specific ensemble skill scores, which will give you information about the resolution of the model, about things like this.
May I ask you another question? How are the hydrological models calibrated?
How the hydrological models are calibrated? I think this answer will be much better answered in the next sessions, which are dedicated to this.
Yes. I'm just wondering if there is also you have chance to do the ensemble with different continuous parameterization from one model only. Like for example, the warp element has different kind of continuous parameterization. Have you tried to run one model with different parameterization? How is it different from model?
Okay, so you are asking whether we can build an ensemble by just changing the parameterizations. Yes, this is possible, and actually we did it. Here it's very simplified, and we only mentioned one member, but there were different realizations. Here it's only we only took the best one, but of course it's interesting to get to have the different members.
Yes. Do you apply any bias correction methods to output of your meteorological outputs? Because modeling means bias.
Yes.
And you have to remove those biases before using hydrological model.
Okay, so you are asking whether we...
How do you believe your meteorological model results? How do you validate?
Okay, you are wondering whether we unbiased the model outputs, the atmospheric outputs. This is not done here because it was done on one case. I think it's more relevant to do it, over a long time, to do some statistical corrections.
But you should, because these hydrological models require bias correction. Because you are using daily or hourly data sets. And you have to compare the observation, you have to detect the biases, and you have to remove all these biases before using hydrological models.
For this case, it would be difficult because, as you see, you can have for instance, there are some models which give zero precipitation over the basin, so it's difficult to calibrate. You can do this, but you have to know the climatology of the model and so on.